Welcome, everyone. We're going to get started in just a minute right now. Welcome to today's virtual consulting office session. We're going to have a couple different presenters affiliated with this project. Let me remind you as we get started that this is a regular Zoom meeting, so you have control over your own microphones. We ask that you keep yourself muted during the presentation. There will be time at the end for you to unmute yourself and ask a question, and you're also free at any point to put something into the chat. If it's if you need to remind yourself what the question might be, put it into the chat. But I'm going to ask the presenters they don't need to get distracted by that. We'll just have time at the end for questions. And all of our VCOs are recorded. After the files are processed, we put them all onto our VCO web page, iGuides VCO web page. And they're always there for your reference later, or for sharing with your students, or however you might find to have them be most useful for you. So let's see, we're going to wait just a few more seconds as people continue to join. Yaoi, I'm going to stop sharing right now, and I'm going to let either of you, whoever might be sharing your slides, can go ahead and get them started. We should have tested that 5 minutes ago before we had an audience here, but our VCOs, we like to, do you have sharing permission?
No, I don't.
Oh, what the heck? Okay, I know the person. We used a different.
Should I send a request?
Yeah. Oh, there we go. Thank you very much. Yep, this is a UIUC Zoom meeting, which I don't have very many options to change things. Did you get the permission to share? Excellent.
Yes.
Perfect. So with that, I will mute my own microphone and turn it over to you to introduce yourselves and carry on. Thank you very much.
All right, thank you, Diana. So, hello everyone. My name is Yaoi Chang. I'm a professor at the Department of Computer Science and Engineering, University of Minnesota. Welcome to today's VCO. The topic here is RegionLM, but the general idea is we have been working on language models for capturing spatial context from geospatial data. And this work and this VCO is going to show you how we take all this pre-trained language model that we have built to be able to consume vector data of point, lines, and polygons and generate embeddings that will be able to use in many different settings. We tested the embeddings for things like mobility, mining, anomaly detection for people's trajectory, for prediction of certain indicators like public health indicators. And I hope you enjoy this VCO. And if you have any questions, please feel free to reach out to me, Ijin or Zekun. And I'll have Ijin and Zekun introduce themselves. They will be the main presenters today.
All right. Hello, everyone. My name is Ijin. I just graduated from the University of Minnesota. I was working with Yaoi, and I'm an incoming assistant professor at the Southern Illinois University this coming fall. And I'm also looking for motivated PhD students working with me on spatial AI topics. Thank you.
I'm Zekun, and I'm also a PhD graduate from the University of Minnesota, working with Professor Yaoi Chang. My research interest is in spatial AI, and I have built language models to encode contextual information for point of interest data. And today we are going to show some applications on how to encode the context and learn about how to apply it to points, polygons, and lines. Yeah. Thank you.
All right, Eugene, it's all yours.
Okay. Thank you everyone for joining today's iGuide webinar, and I'm going to introduce our work, RegionLM, which is an approach to integrate point, line, and polygon context for urban representation learning. And this webinar is designed as an introduction, so even you're not familiar with urban representation learning, you don't need to worry about it. We will start from very basic concepts before we move into the methodology. And after the slide presentation, talking about all these concepts and the methods, we will move on to a practical session to show you how can we do urban representation learning with real world data with the method we talked about. And that will be led by Dr. Zekun Li. So let's first talk about what is urban representation learning. Well, the goal is to learn general purpose regional representations from multimodal urban data that can summarize the characteristics of a region or a location. And to be able to do this, researchers combine many different types of urban data. For example, we can use satellite imagery to understand land cover, or street view images to capture what people see on the ground. And also we have texture data like reviews, sensors data to describe human activities. And also we have structured geographic data from sources like OpenStreetMap to describe what's in a region and how they are organized. So each of these data sources tell us something about the city region in very different way. And in this tutorial, we will focus on one particular type of data, the structured geographic data. And this will include geographic entities such as buildings, roads, parks, stores, or many other map features. And these data are widely available through many sources like OpenStreetMap and other government agencies. So our goal today is to understand how we can represent these geographic entities and combine them into useful representations for other downstreaming tasks using machine learning. So before we get into how can we do that, let's first answer why do we care about structured geographic data? Why are they so important? So different from data like images, these geographic data can explicitly describe individual geographic entities. For example, in this figure here, we have a coffee shop represented as a point, a freeway represented as a line, and a shopping mall represented as a polygon. And these different geographic entities form or are organized like this to form this neighborhood. And each entity has its own properties and the relationships to the nearby entity. So we can describe their relationships. So such descriptions, such rich descriptions make these structured geographic data especially valuable for understanding urban environment. So the first important piece of information in these geographic entities is their semantics. So basically, each geographic entity has their own attributes that describe what it is. For example, the point whose name is Starbucks here is a cafe, and the point Apple Store is a retail store. Also, like the shopping mall named Westfield Mall, its type is a commercial area. And the road I-80 is a freeway, or we can also call it motorway in OpenStreetMap. So this type of semantic attributes provide us very important information, telling us the functionality of a place or an entity. So understanding these meaning is very important to build a model for urban representation learning. And besides the semantics of these geographic entities, these geographic data also describe the spatial geometry. For example, the line and the polygons describe the shape and orientation of the entity, or like the distance between two entities. In this example, from like the polygon geometry, we can know that like the Westfield Mall is about 1 million square feet large. And the Westfield Mall is about 120 meters from the parking lot, and parking lot is located in the east of the mall. So we can tell these spatial relationships from the geometry of these geographic entities. And these spatial relationships help us understand how these geographic entities are placed and organized in a place, which is very important for us to understand the environment. And another important thing we need to consider is the topology. So the topology basically describes how geographic entities are connected or related. For example, in this case, the coffee shop is located inside the shopping mall. While if we have another road, for example here, we can say two roads are intersected each other. So these topological ships are often very informative to describe an environment. So here we have talked about the semantics, the geometry, the topology of these geoentities, and together they provide a rich description of the geographic environment. So we basically want to encode all this information to be able to represent the urban environment. But now let's think about a question. Given these geographic data, is modeling individual entities enough? So let's look at an example here. Suppose we have 3 coffee shops, one inside a shopping mall, another is in an airport, and the third one is near a university. Do we expect to use similar representations to represent them, or more intuitively, are these coffee shops similar, or will they share similar visiting patterns? Well, probably not. Why is that? So, because their surrounding environments are very different, and those environments will strongly influence how people use these places or geoentities. So, the coffee shop in the shopping mall will be very different from like the visiting pattern will be different from the coffee shop in a university, even both of them are coffee shops. So this actually illustrates a very important concept of context. So as a human, we do not understand a geographic entity by itself. Instead, we naturally consider what surrounds it. And when people or someone says, "Oh, there is a coffee shop," and we will ask, "Oh, are you talking about a coffee shop inside a mall or near a school or something else?" So as a human, we care about context. That's why if we want the machines or models to understand the geographic entities, we should also provide information about their neighboring geographic entities. That's why when we do urban representation learning, we want to include these context information in the representations as well. So how does this existing work represent the geo entities? Well, there have been some work focusing on encoding the geometry itself, methods like space-to-vect or poly-to-vect. They focus on representing these lines, polygons, the spatial coordinates, or geometric shapes from these geo entities. And these methods are good at representing an individual geographic entity, their spatial locations, their shapes, but they do not consider the semantic information like the name and types of these geographic entities. So if two locations are having similar are having similar geometry or at the similar spatial locations, but if they have completely different functions, they might end up with looking very similar to the model. So the second category of the methods incorporate semantic information like SpaBERT and GeoLM. These models are developed by Dr. Zokunli. And so in these models, instead of considering only the geometry, the coordinates of these geographic entities, they can represent the point of interest POIs, typically points. And these methods combine texture information and basically their semantics and their coordinates to represent POIs. So the semantic information helps distinguish places and that are like at similar locations but having very different functionalities. And in these methods, they also consider the context information, like for a target POI, it will consider the neighboring, what's the neighboring POIs to be able to contextualize the target location. However, right now, these methods still focus on purely point-based entities. But as we mentioned, in a city, we have many different geographic entities that are not points, like roads are lines, buildings and parks, or land use are polygons. And these entities are also very valuable to describe the surrounding environment. So we still need a better solution to be more flexible on different types of geographic entities. Well, there are also methods that consider or combine multiple types of geographic entities like region DCL. It's rather than representing a single POI, it combines building footprints, which is polygons, and its neighboring POIs, which are points. So it does have some way to combine two types of geographic entities, but in these type of models, they typically focus on specific types of geographic entities and handle them in separate ways. For example, I will have a model or or uh, or a method to handle building footprints itself and handle the POI itself, and then combine these two embeddings. But it does not fully represent the interactions between these geoentity types, and it cannot flexibly extend to other geoentity types like rivers and roads. So there's still a lack of consistent ways to model these different geographic entities. So in general, these existing methods mainly model individual geometry entities or types and do not effectively learn cross-type relationships between these entities. So in our method, we would like to build a unified model that can learn from all of them, that can be more flexible to handle all types of geographic entities. So this leads us to RegionLM, and let's see what's RegionLM, our proposed method. So the main goal of RegionLM is that instead of representing only one geographic entity or one type of geographic entities, we want to learn a representation that can combine information from all of them, from points, lines, and polygons together in a very flexible way. Once we can learn this, we can generate the representations for these geoentities. They can be used for many downstreaming tasks like mobility prediction, anomaly detection, or other urban AI applications. And yeah, so this is the goal of RegionLM, and let's see how RegionLM can do this. All right, let's begin with a simple example. In this figure here, suppose our target entity, or let's look at Starbucks here. Around it, we have several different geographic entities. There is a shopping mall represented as a polygon, and a nearby Apple store represented as another point in a parking lot, and a freeway represented as a line. So as a human, we can naturally understand this entire thing together. So this is basically a commercial area, and when we are talking about, oh, Starbucks is inside a shopping mall near a freeway, we can immediately build a picture of this location. However, models cannot naturally understand these relationships. So for model, points are just coordinates, lines or roads are just line segments, and buildings are just polygons. So before we ask the AI model to understand these neighborhoods, we first need to convert this like heterogeneous data into a common representation so that the model can consistently process it. Since points, lines, and polygons have completely different shapes, if we directly feed these different geometries into a model, it will become very difficult for a model to process them. So instead, we first convert them into a consistent spatial representations. Excuse me. So the first step here is to rasterize lines, polygons using a spatial grid system such as GeoHash or H3. Here specifically, we will use H3 for illustration. And H3 is an open source hierarchical spatial indexing system originally developed by Uber. And normally we will divide the word into squares, like geohash. So hexagons are different. They have several nice properties. For example, each hexagon cell has six, like here, each hexagon cell has six equally sized neighbors, and this will make neighborhood analysis more consistent. And the hexagons also avoids some directional bias like the square grids. Because the center of the hexagon has equal distance to each vertices. So to use these hexagons, we will replace the original geoentities with these hexagons. So instead of remembering the exact outlines of the roads or a building, we can simply record which hexagon cells they occupy. So in the roads, which is a line here, we can add some buffer to it and see what are the hexagons that are intersected with the roads, with this road. And similarly for a polygon, we can also use the hexagons to see what are the hexagon cells that are covered over this polygon. And each hexagon cell here will inherit the semantic information of the original geographic entity. So for example, this building, shopping mall, all the hexagons here will have the same semantic information, which is the name will be the Westfield Mall and the type will be a commercial area. So this way allow us to encode these or to represent these points, lines, and polygons to be represented in a unified way. So now we have unifying all these geometries. We also want to integrate these inconsistent schemas in the attributes. For example, we might have names, types, or in some, or we might have multiple sources of geoentities represented in different ways. And to convert these heterogeneous attributes into a unified texture in format. So we basically convert these heterogeneous attributes into this unified texture format. For example, we represent each entity as a simple text pair like Starbucks, column, cafe, for one entity, and Westfield Mall commercial area for the shopping mall here, and the I-80 motorway for the road here. So even if we have other types of semantic information, we can basically treat it as more attributes for in this for each entity here. So now for each geographic entity, regardless its geometry or its original attributes, we can represent them consistently. And we will use these new we will use these new geo entities and the semantics in the machine learning model. So we will so the next step is for each target geographic entity, we will naturally form a sentence from its neighboring geo entities based on the distance. In this case, we will write a sentence with geographic entities, just like how we write a sentence with words. So let's start to use Starbucks as our example. We place Starbucks as at the beginning of the sentence as a pivot, and our goal is to contextualize it to understand if we're standing at the Starbucks, how can we understand the neighborhood environment? And the sentence will start with a CLS token representing the beginning of the sentence, and then we put the semantic information that we have formed for the Starbucks. And next, for this target geographic entity, we collect all the surrounding entities and organize them according to their spatial proximity. So in this case, our target is Starbucks, and its neighborhoods includes like the Westfield Mall, the Apple Store, and I-80 freeway, and Oak Street parking lot. So these entities are separated in the sentence using the SEP tokens. And in our earlier rasterization steps, a line or a polygon has been represented by multiple H3 cells, and each H3 cell is treated as will be treated as a separate geographic entity and inherit the semantic attributes of the original entity. So this is why the Westfield Mall and the I-80 or the parking lots might appear multiple times in this sequence. So each occurrence here actually represents a different H3 cells belonging to the original mall or roads. And then we organize these new geo entities in based on their distance to the target, and the entities that are closer to the Starbucks will appear earlier in the sequence, and the distance entities will appear later. So this resulting like this sequence looks very similar to a sentence in natural language, right? However, instead of the words, each token here actually represents a geographic entity or an H3 cell derived from the original entity. So with this sentence, we might naturally think about, oh, we can use a language model, and we expect the model to be able to learn for the target location from the geographic entities surrounding it in this sentence. However, in this sentence right now, we only have the semantic attributes of the geographic entities, which is not enough for the model to understand a geographic location. The model also needs to understand the order in the sentence as well as the actual location of these geographic entities in the space. So for each token here, our model will combine actually three information. First is the token embedding from this the token embedding that represent the semantic meaning of an entity like a Starbucks, the shopping mall, in this sequence. And the second, we will have the model will input the sequence position embedding, which is also used, which have been commonly used in the standard language model, telling the model where the tokens appear in the constructed sentence. And third, which is new here, we will add a spatial coordinate embedding. This is a geographic component, and it encodes the actual location of each entity in the space. So in this way, after having the spatial coordinates, it will capture the relationship between the spatial relationships between the geographic entity here in the sentence. So by adding these three embeddings together, each token actually tell the model what is the entity and where it appears in the sentence and where it's located in the geographic space. And this allows RegionLM to preserve the language model structure as well as explicitly incorporate the spatial information. So after we have this input sentence, we can input it to the RegionLM, which we are going to use SpaBERT here. So remember that original SpaBERT only encode the POI information, but right now, after we convert the line and polygons, we can the SpaBERT here can consume more types of geographic entities. And unlike other traditional region representation methods that can describe very limited types of geographic entities, RegionLM can cover more types of geographic entities. And after the SpaBERT model, this embedding will summarize its surrounding neighborhoods, which includes both semantic and spatial relationship to its neighborhood. So we are able to answer the questions from this embedding here, like what kinds of places are surrounding these locations and how they are organized or arranged. So after we generate the POI embedding for each POI, we can then aggregate these embeddings. So for each target POI, we will generate a sentence and passing through the SpaBERT to generate an POI embedding. And then we can aggregate them to represent an entire neighborhood or region. And once we have these region embeddings, we can use them to do many different downstream applications. So one example will be after we have these embeddings, we can simply look at them by visualizing is there any clustering pattern in these embeddings. So in this example, we can apply a dimension reduction and a clustering algorithm to understand the embeddings from RegionLM. And in the later practical session, we are going to see this type of clustering pattern. For example, we can see some red and blue clusters here in space. So we are able to see some we are able to see this type of clustering patterns from these embeddings, and then we are able to dig into these clusters to analyze what's exactly caused these clustering patterns in the environment. And of course, we can apply this type of embeddings to more complicated applications like mobility anomaly detection to identify abnormal human mobility trajectories. And in this work, we can replace, for example, we have these coordinates along the trajectories, and normally we can use the raw POI categories or just the pure spatial coordinates for each location in the trajectory. But right now we can replace them with the embeddings from the RegionLM to contextualize each location in the trajectory to identify, to better understand the trajectory of a human. And this will be an interesting application to apply our this new embeddings. So so this will conclude the introduction of what is urban representation learning and how can we use a language model to integrate these different types of geographic entities for urban representation learning. And in this tutorial, we have our slides in the iGuide platform, and you can simply search RegionLM in the platform. And also we have the notebook tutorial that show you how can we really convert what we have talked about conceptually to how can we really see the clusters with our code. And we are going to use OpenStreetMap, which is an open source map data, and it provides point, line, and polygon map features. In this demo or tutorial here, we are going to use the POI and land use and buildings as an example. And for lines, we have also talked about how we can convert it using H3 cells. So it's quite straightforward to add more geographic entities in for the RegionLM here. So in the OpenStreetMap, for points and land use, if we show it in a table, we can see these these entities in the OpenStreetMap having the type and or it calls F class here, as well as the name of the geoentity here. So even though for some entities we do not have the name for it, since we construct it as a sentence, we can simply skip it in the sentence. And to narrow down the scope of the study area, we further filter out these geographic entities in the New York City region to see how we can produce the embeddings for all the POIs in the New York City and do clusterings to identify what will be the clustering pattern from these for the regions in the New York City. So this concludes the slide presentation, and I'm happy to answer any questions from the audience. And the next, Dr. Zokun Lee will lead the practical session using the notebook.
Thank you, Ijin. That's really interesting. I'm looking forward to seeing this work. I don't know currently whether the notebook is It's on the iGuide platform. Eventually, it will be kind of cross-tagged across notebooks and open educational resources because this project is part of our, I didn't say this at the beginning, this project is part of our UCGIS Community Champions program this year.
Yeah, we have already uploaded the slide to the platform as well as the notebook, and they are linked.
Yeah, excellent. Okay, I'll go back now, and I want to watch the demo.
Yeah. So now we are going to have the second part of our workshop today. And this is going to be a very interactive session. So it means that it will not be just me executing code. And everyone here will also try to execute the code and see the outputs from your side. And we are going to have a very low pace tutorial. So if you have any questions, any steps that you are stuck on, just feel free to interrupt. Just before we begin, just want to show you what we have here. So we have uploaded this tutorial to the iGuide platform, and I just shared the link in the chat, and you will be able to see this full tutorial and copy paste the code and execute in your either terminal or VS Code or any other IDE that you are comfortable with. Also, at the bottom of this page, you will see this educational resource. This is the slides that Yijun just presented. So if you click the link here, you will see the exact same slides that Yijun showed you. Okay, now let's get back to the notebook. Okay, so this notebook lists all the steps that are required to go from OpenStreetMap raw data to a final visualization that shows you the clusters of those POIs in the embedding space. It shows you how the model understands those embeddings. And before we dive into the code, I want to ask two questions or to do two polls just to understand our audience coding capability. So my first question is, I wonder how many of you have used Python, like either for projects or course projects, like for research or just for fun. Anything just counts. So if you have used Python, please use Zoom interaction. Like if you go to the bottom of your Zoom window, you will be able to see React. So there's a heart. If you click that button, and just to give me some reaction, then I know you have used Python before. Okay. Four people already. 5, 6. 6 people. Nice. Yeah. We have a pretty solid coding group here. But for people who haven't used Python, no worries at all. This is not a prerequisite. You can just copy paste the code, and I will explain the purpose of the code, and you will not be struggle at this. And my second question is, how many of you have used PyTorch? So even if you have just typed in import torch in the Python and executed it, that still counts. 2, 3, 4. And we have a very skilled person, Alex, who also gave himself a round of applause for very proficient PyTorch skill. Okay, nice. So for people who have used Python, I suspect you already have Python installed on your own machine or any IDE that you are comfortable with. And for people who have not used Python, you can use Google Colab or Jupyter Notebook, those online tools to try to execute this code. So with that being said, we can get started and to look at the code. I will now repeat the things here in those big paragraphs, and so those are already covered in Ijin's presentation, and we'll starting from here, the prerequisites. Okay, so the first step is that we need to pull this GitHub repository, and we have the source code already hosted on GitHub. And you will also be able to see the exact same tutorial if you click this 0 RegionLM tutorial. So you can either use the iGuide or just copy paste it. By the way, the iGuide is also linking to this tutorial. So you are seeing the exact same content, no matter which page you are referring to. So for people who have used, yeah, the first step is to do a git clone, and you can do that in your terminal or IDE. And if you have, so I'm going to pause and wait for 2 to 3 minutes. And if you have completed, you can give me some reaction. Then I will know you have completed. And if you have any questions, you can raise your hand.
So Zayakun, I don't know how many of the audience had expected to be working on this demo alongside you. We'll see how many people. The iGuide platform is in heavy use right now because we're in the middle of our summer school, and that shouldn't affect at all the usage right here, right now for this group. But when you've gone through this particular tutorial in the past, how long might people expect that it might take, just to give people a sense? Frequently, our VCOs just go on only for about an hour. So I just wanted to check in with you about that.
Oh, I see. So for me, if I execute this code, it will just take 10 minutes. But it depends on how fast people will be able to copy paste the code.
Right.
Sorry, maybe I have the wrong understanding of time span. I thought it's going to be a 3-hour session. So if we only have 1 hour in total, then I'll just go through those steps and then explain what the outcome might be.
I'd love to be here for 3 hours, but I don't think my students upstairs would it would work very well in the summer school. How about, for the sake of this presentation today, we're going to make sure we share with everyone here the notebook where it is on the platform, and they'll have the recording of this that they'll be able to watch your steps. But I think for the sake of time today, we're going to I'm going to ask you just to go through and show it on your own screen to demo it for the rest.
Got it. So we have 7 minutes left.
Yeah.
And
we can go a little bit over 12, but
it's okay.
Hour,
I'll try my best to conclude in 7 minutes.
Thank you.
So yeah. Basically, step 1 to 3, I have already done it on my side, and I have downloaded the data sets and pre-trained ways and organized in this way. So if you want to do it by your own, you can download the data and structure it in this, like in this folder. So we are going to run through the steps to extract the features from the downloaded data. And the way to do that is just copy paste the code here. So once you have pulled the code from GitHub, then you will enter this UCGIS community champion folder. Let me do the conda activate. Okay. So what this step is doing is this is preparing the POIs in the region that we want to process. And it's going to repeat this for POIs, the buildings, and the land use data that Yijun just told us. Basically, this is looking at the NYC data region, and then to select the data to select the subregion that we want to work on. Okay, I think I already have this file processed. If you execute from your side, it will take about 2 to 3 minutes to finish these 3 scripts. And our second step is to do rasterization. Basically, after the first step, we only have the points, polygons, and so they sit separately. The way to convert them into a consistent format is to convert it to H3 data stream. And we call this step rasterization. For points, we will rasterize it into a H3 hexagon cell. And then for the land use data, which is polygon, we are going to have a sequence of strings that describes the entire polygon. So I'm going to do it for the building, and I will skip it for the. I will do it for the point.
Sorry, so building is polygon.
Oh, sorry. Building, yes, building and land use are polygon, POIs are points. Okay, so after we finish these 2 steps, we are going to merge the building and land use. Since they are both polygons, we will merge it into an AOI file that gives us the contextual data. And if after we process this step, we can see the content of this CSV file output as a table like this. We will have OSM ID, its category, geometry, and H3 list. So H3 is the hexagon cell that tells you which hexagon on the map that it corresponds to. Then we are going to use that processed table to prepare the input for SpaBERT. Okay. So now this step is completed, and in this step is going to what we call linearize this input into a SpaBERT format. So this is a language model that takes in the CSV file and prepare the coordinates and the names and type of the POI. Okay, and then the most time-consuming step is the training of SpaBERT. So this will take about 30 minutes on my machine, so I'm not going to execute this code here. And then for prediction, it will be much faster. It takes about only 5 minutes on my side to apply this model on this region after the model has been trained. Okay, so I have completed 1.4 on my side, and I'm skipping 1.5. And then so after step 5, we are basically getting the embeddings of the POIs. Then on step 6, we will group the POI level embedding by region. So now we are getting region level embedding. We have some parameters in this configuration file, and you can adjust which geographical hierarchical level that you want this embedding to be aggregated at. So a smaller number means a larger region will be aggregated. Then for the next step, we will do a dimension reduction that is for visualization and the clustering purpose. So in this step, we will want to understand how the model interprets the embedding and how similar one embedding is to another embedding. And on the step 8, we will do the cluster visualization and see if we have completed this. Okay, not yet, but I have the visualization already pre-run So as I mentioned, this parameter is going to control which level the embedding is aggregated at. So I have changed it to Z10, Z11 and Z9 to show you what the embedding will look like. So here is the NYC region that we, okay, so in the terminal, it already completed this part, but I'm not going to execute the following steps. Just to show, I just want to show you what the final output look like. So here, each POI or region embedding, it has a unique color. So the POIs with the same colored cell means that the model thinks they have similar characteristics. So based on this picture, we can see that this purple color usually aggregates at the main streets. So you will see a lot of purple color, and we have very dense, we have very dense region in the downtown area. So I would suspect this purple color means very crowded area, like a building very close to each other, or building with that hosts multiple POIs with diverse purposes. And another interesting thing is here, this blue region, which corresponds to a park. So you can see some aggregations of the clusters in this park region. And here you will also see a blue cluster here, which is also a park if you look at the map. So this is what we can observe in the Z11 level. So this is the final level. And then in the more coarse level, you can see these hexagon cells got bigger. So because it is 2 levels higher than Z11. So here you can see the purple color or purple or bluish color start to dominate this region. And this is where the rows are the densest. And then so outside of this region, the rows will be much sparser. So you can see some consistent characteristics here by looking at even higher level. Yeah, so this is what I want to show you guys. And if you execute the code from your side, you will be able to see the similar output as here. And I'm going to stop and check if the audience have any questions.
Any questions from the group? I am really glad to know about this. We have one of our summer school teams here at University of Illinois right now that is using specifically POI data from OpenStreetMap, and I'm excited to let them know about what you've developed here.
Yeah, OpenStreetMap is always fascinating to analyze.
Yeah. Any questions from the audience? Let's put these links in the chat again so that people have them now. So that we've got, I think everybody has been here long enough to have seen the one in the chat before. That's one of the notebooks. What I had mentioned earlier is that this Yaoyi's activity this year falls under our open educational resources. So you can see right here too how the slide deck that's being demonstrated, that's being displayed right now on your screen, comes from our open educational resources, and this is very common to have slides that might be able to help an instructor present about some background around this, also be linked directly to a Jupyter notebook that can be used to support a hands-on activity. That's what the iGuide platform was designed to do, to have these linked knowledge elements. Well, if there aren't any questions right now, thank you for letting me, I'm sorry I had to rush this through at the end. I know if it would be very interesting for people to be able to work with this notebook, and I hope we get you some good feedback soon from the different audiences that are going to explore it.
Thank you so much.
You're very welcome.
And Eric, for all
okay.
the information.
Oh, is there a question? I didn't see. No, yes. Okay, so we're going to wrap up this VCO for now. Remember, I did say this is all being recorded. It'll be up on the iGuide website soon. Thank you all for attending. We have upcoming sessions pretty much almost every week. We will have ones between now and into September, through August and September. So pay attention to those announcements that go out about those. And thanks everyone for joining us today. And we'll see you soon. Bye-bye.